Okay. So guys, drawing free body diagram worksheets. We did it last week on Cami. For this assignment, we are going to do the drawing portion on Google Docs. So to draw this, a book is at rest on a tabletop. So a free body diagram would look like what? So what we're going to have to do here is you're going to insert drawing, new. All right, so we can't scoot this away. Actually, we can a little bit. So a book is at rest on a tabletop. All right, so something's at rest on a tabletop. So we're gonna draw a free body diagram. Go to shapes, draw a circle, or a square, Jesus. All right, fill color, we're just gonna keep it transparent. Draw a circle, or shapes, you can go circle, whatever, in the center. Do it as best you can. If it's not perfect, it's not that big a deal. Okay, and then we're gonna click out of that. Now we're going to go to here, select line, and we're going to click arrow. So the one thing that we always know is acting and it goes straight down is gravity, F sub G. And then if it's at rest, we're going to click from the center, and we're going to go straight up till they look about the same length here. Okay. If they're not the exact same length, you can click on the arrow after you hit the select button, and we can shrink it a little bit if needed. Okay, so to indicate that these two things are the same length, line, and we're supposed to make just two lines going through the thing. Come on. To represent that they're equal. Those, I do not like how they look, so I'm going to erase those. Okay, line. Why is it doing that? I don't want it to do that. I want line here. Okay. I want a line here. Cool. And same thing down here. I want a line and a line going through, telling us that those two things are equal, and we got to add our text box to let everybody know what these things are. So we have F sub G. To get the subscript, it's control comma, and then up top, F control comma to get the subscript is our normal force. Okay, so select arrow to click out, and this is what we're looking like. See if I can get the little circle guy and move it over just a tad. Nope. All right, looks good. Save and close. All right. We have an egg that is in free fall from a nest in a tree. So neglecting air resistance. This is like the one last on Friday from Cami. Okay, we're gonna, what is it? Excuse me. Insert. Drawing. New. Square represents whatever our object is. We got a little center piece for our circle. Wait, what happened to my square? Transparent. Okay, whatever. Line or arrow from the center, make it go straight down, because gravity is always acting on something when it's on Earth. And so air resistance would act to the opposite of that, because air resistance is a type of friction, which would go against motion. But since it said neglect air resistance, so guess what? The only thing that we have is the force of gravity. So F control comma sub G. Boom. Save and close. Okay, flying squirrel is gliding, no wing flaps, from a tree to the ground at a constant velocity. Consider air resistance. Okay, so a couple things in here that are keywords. Constant velocity means straight line, constant speed. So that is telling us that the body is in a state of equilibrium. That is called dynamic equilibrium. So that means everything has to balance out. So for a free body diagram, we're going to say the squirrel is gliding down pretty much straight down. Okay, and we're going to consider our air resistance. So we're going to insert drawing. I'm going to start with our box to represent this flying squirrel. Make the fill transparent. Okay, next thing. Going to make our little circle in the center, or close enough. And then we're going to insert our arrows. So we have, why does it not go right where I want it? I click. Okay. So we have force of gravity. But it says we have air resistance going on as well, and that it's constant velocity. So constant velocity means the forces have to balance. So from here, we got to make it look like it's about the same size. Nope, don't want that. This one maybe just looks a tiny bit lower, so let's increase the size of that just a tiny bit. Okay, it looks good to me. So to show that these two things are equal, we're going to go to line here. Showing us that these two forces are equal. And add the text box. So first one down here, we have F control comma sub G for the force of gravity. And then up top, we will have F, and since it's air resistance, you could write sub air. And that is good. So this is telling us that, all right, the body is in equilibrium. The net force is equal to 0. So it doesn't mean that there's no motion. It means that there's no change in motion. So that means it has to do basically one of two things: being at rest or constant velocity, which is a straight line, constant speed. We have a rightward force being applied to a book. Now, in order to move it across the desk with a rightward acceleration, consider the frictional forces. Neglect any kind of air resistance. Okay, so it's on a desk. So if it's on a desk, it's not moving up or down. So that's important to know. We're going to draw our book. We're going to select the box here. And we're going to make it transparent. So you're going to go to circle somewhere in the center. Close enough. Okay, so one force that we always have on Earth going from the center. Don't like how it's there, not in my center. Click. What the heck? Come on. Bruh. I don't like that. It's annoying me. Okay. So we have our gravitational force going down. Again, since we're on top of the table and this thing is not moving, we have our normal force going up. And those two things have to be, those two things have to be equal. They absolutely have to be equal. So we have F controlled comma, so normal force. We have F sub G. And these two things are going to need to be equal. Why is it being a scutch here? All right, that's not irritating. Whatever, I'll put it inside then. Can I do that? Are you gonna let me do that? Line, for the love of goodness. Okay. All right, so that's telling us that these two dudes are equal. The normal force, gravitational force. Okay. Let's see, can I move this for a second? Let's save and close. What else is going on? There is going to be friction force, and then it also says it's going to have a rightward acceleration. All right. So if it's going to be moving to the right, we need to have a net force going to the right, which means there's got to be a force obviously then going to the right, and it's going to have to be bigger than the friction force. Now, friction force, why is it left in this case? Because it's going in the opposite direction of motion. And it's going to be smaller than that guy because we need a net force in the direction of the motion. So the push force or whatever, we have been calling it the applied force. So F sub APP or F sub A, doesn't matter, either one works. And then for friction, F sub lowercase f. Now I can click on this dude and make it upward a little bit. Okay, so this is showing what? Normal force, gravitational force, the lines here, the equal lines, telling us that those two balance each other out. We're not worried about them. The applied force, you can look in the picture and you can see that it is larger in magnitude than the friction force. So that means that there is going to be a net force in the right direction, and it is going to accelerate to the right. Number 7, a rightward force is applied to a book in order to move it across a desk at a constant velocity. Again, consider friction forces neglecting air. Okay, so it's going to be very similar to this. So what I'm going to do is I'm going to go back in here and I'm going to highlight this whole thing, just drag and click, right? So from the top, literally I just exit in here and I just click down and I drag. I'm going to hit Control C, save and close. Okay, I'm going to go here. I'm going to hit Control V. Oops, that didn't work. So let's exit. Let's hit the backspace. Let's try going into Insert, Drawing, and then pasting in here. Okay, here we go. We got it. So in which case, since this thing is moving at a constant velocity, the net force has to be equal to 0. So this applied force arrow, yeah, we're going to have to shrink this dude. So it looks like it's about the same length as my friction force. Okay, that looks good enough. And now I'm going to insert 2 lines to show that these two dudes are equal. Why are you being a scotch? Click line, okay, down. It's not where I want it to be. Stop that. Click down, cool. So this is telling us that the normal force, gravitational force balanced out. Friction force and applied force are equaled out and balanced. So if you were to just look at this picture, you couldn't fully tell me whether or not the object is in motion or not. All I know for sure is that the net force is equal to 0. And from this, that means, well, there's no change in motion. Doesn't mean that it's moving or not moving. It could be either at rest or constant speed and in a straight line, which means a constant velocity. So just by looking at this picture, that's what you 100% can say. You cannot say with 100% certainty that it's at rest or that it's moving in a constant velocity. You would need a little bit more information by reading through the problem. But that is going to be your drawing for this one. Number 8, a skydiver is descending with a constant velocity. Again, big time idea here, considering air resistance. All right, so insert drawing. And here we go. Shapes. No, that's text box. Shapes. Square. Box. Fill color. Transparent. Circle. Shape. That's what we want. Centerpiece. Or close enough. Again, if it's not perfect, guys, don't freak out about it. Okay. What is the one thing that we're always going to have? Gravity. And what else is going on here? Gravity down, and it said that this is moving at a constant velocity as he's falling. Again, so it says to consider air resistance. Air resistance is a type of friction. So if I draw in my arrow here, click on that. So now I get the little black plus sign, go from the center, and I'm going up. I want to try and make it the same length or very close to. Looks relatively close, and if I hit the select button and drag it, okay, it looks pretty good. But what do I need to do to make sure that these things are equal? All right, I need to add in just those two little lines. Now, where is this thing? Now, what if I wanted to do? You can even just do this to make it easier sometimes. Scribble. Oof, that was bad. Scribble. Yikes. Hey, what the heck? Why is that? I don't like that. Oh, yeah. Up. All right. Well, I'm just gonna try the line thing again. That is an arrow. I want a line. Hello, line. Okay, let's do this. Sorry that this is being a pain. Okay, so we have our weight going down, our gravitational force going down. So we have F, control comma to get the subscript. And okay, well, what is going on? It said to consider air resistance. So this would be F sub air for air resistance. Now this is telling me that the net force is 0. The net force of 0 meaning there's no change in motion. So again, I could be either at rest or constant velocity. Now, from the problem, all right, we would kind of know Skydiver is descending. So we are moving at a constant velocity. Net force is 0. Both the air resistance and gravitational force balance each other out. Force is applied to the right of a drag sled across loosely packed snow with a rightward acceleration. So it's not very, very packed snow. So if it's very, very packed snow, it'd probably be able to move faster. So loose snow, I would say we're going to have some sort of friction here, this resistance. So we're going to go to Insert, Drawing, New. Transparent. Give me my circle quickly. Instead of line, I want arrow. Okay, so from the center, gravitational force going down. Now, notice that they were talking about acceleration in the rightward direction. So that means there is no acceleration in the y direction. So that's the up and down. So that means those two things have to balance each other out. If they balance each other out, that means that the gravitational force and the you're on a surface, that will be the normal force. Those two things have to be equal. So we have our normal force, and over here, gravitational force. So I'm going to save and close for a second and go reread the problem. And it's moving to the right, and it has a rightward acceleration. So that means there needs to be an applied force going to the right. And then what else does that mean? It means it said there it's going through some loose snow. So that's telling me that there is going to be some sort of friction. Not a lot, but there's going to be a little bit. Select, drag that down just a tiny bit. Okay, so this would look, if you were to just look at this, if these two are equal, this right arrow, this applied force, looks like it is going to be larger than the friction force. And if that's the case, the net force would be in the rightward direction. So here's our applied force. And then we have F sub F for our friction force. This is greater than the magnitude than this guy. So the net force is going to be in this direction, whatever the difference between those two values are. And it's going to be in this direction, meaning it's going to accelerate to the right. Okay. Number 10, it says a car is coasting to the right and is slowing down. So draw a free body diagram for this. Okay, so if it's moving to the right, what direction does friction have to be? Friction always acts opposite of motion. So if this thing is moving to the right, friction arrow is going to have to be to the left. It's on a flat horizontal road, so normal force and this guy here, gravitational force, are going to be equal. So what I'm going to do is I'm going to copy this, just highlight the whole thing, copy this, and then I'm going to go down underneath here and paste. And I should be able to edit this. So if I click on it, edit. So it says we're coasting. So that means I'm not adding on I'm not hitting the accelerator whatsoever. So this arrow can get goodbye. I clicked on it and then deleted it. This text box here, I can click on it and delete it. So the normal force and gravitational force are equal because there's no acceleration in that direction. And right now, that means there's only one force on it, F net, of the friction force. They're going to be equal to each other. So this is going to cause the object to slow down, okay? It's going to cause it to slow down. Now, again, reading the problem, the car was moving to the right. Friction has to go in the opposite. And since the net force in that direction, it's accelerating it towards the left, or in this case, meaning it is slowing down. And boom. Okay, so that, guys, is how you would come and solve for these missing pieces. All right. All right.